This video lecture will discuss Chapter 2, which is a review of basic statistical concepts. So what we're going to be talking about here, some basic definitions that we should be familiar with. We're going to review frequency distribution, how to create a histogram, and I'm going to show you how to do those in both Excel and SPSS. We're also going to talk about the normal distribution and the central limit theorem and when to use T versus Z testing. Then we're going to discuss hypothesis testing using a single sample and then comparing the hypothesis test of comparison of two different means. So basic terms that we should be familiar with: population. A population will be defined as the collection of all items of interest to the researcher. So this is all of the data that you could possibly gather. It's the entire universe of observations. It's not something that is actually accessible to you. So if you wanted to know the height of every single woman in the world, that's not really something that's possible for you to discover. So in order to test any kind of hypothesis or draw any kind of statistical inference or conclusion, what I would need to do is gather a sample. So you could gather a sample of different women's heights. So from all of the women that you know, or all of the women in a specific location, something like that. So a sample is chosen and used to describe the population. And what we can draw from that are statistical inferences. So these are basic ideas that we get, that conclusions that we can make based on the sample about the population. So we can think of the average, what is the distribution, things like that. And we generally describe these using descriptive statistics. So descriptive statistics, what you would normally think of: mean, median, variance, standard deviation, and then characterizing them using a histogram. So mean, the average; median, the middle value; variance, the rate of dispersion, the risk of not getting what you expect to get, and that value is squared. And then standard deviation, the variance, but in terms that we can actually understand, because let's face it, no one understands percentage squared. So let's look at an example of a frequency distribution. So here we have the tabular representation over here. That's the frequency distribution, and then the graphic is actually a histogram. So what we're looking at here are 5-year returns of a series of different funds. And we can see that 5 funds returned between -4% and -8%. 34 funds returned between -4% and 7.99%, things like that. And that frequency distribution is used to develop a histogram. So your histogram is a graph of your frequency distribution. If it has a positive skew, it means that your mean is greater than the median. And it would mean that, therefore, it would be asymmetric with the tail towards positive values. If it had a negative skew, the mean would be less than the median. It would have an asymmetric tail towards negative values. So if we want to follow a standard normal distribution, what you would normally think about, that classic bell curve, you would expect to see most things centered around the mean. So the highest value would be the mean, and then it would be relatively evenly dispersed from side to side based on that. So what is the official way to calculate the frequency distribution? Well, there's all kinds of different ideas that go into this. Your textbook goes into a description of how these things are calculated, and they're actually quite clear about the idea that, people have different ways of doing this, and you can't necessarily say that, which bin width is appropriate and all that kind of stuff. So 3 steps are necessary to determine the classes of frequency distribution for quantitative data. The classes being the number of groupings and the size of those groupings. So if we would review here, this one had 1, 2, 3, 4, 5, 6, 7 different classes of groupings. Okay. So the number of bins is the number of non-overlapping classes. That can be estimated using the square root of the number of observations. But that's not necessarily going to give you a perfect number. In general, you want to have more than 5, but less than 20, something like that. So that'll just give you a basic approximation. And then, of course, you need to round that to a round number. Then you need to determine the width of each class. So once you have the number of bins, you have your denominator here. So the width of each class would be then determined by the entire distribution of your data. So in order to find that, you would need to have your highest value from your data and your lowest value from your data. So what we're doing here with this width of each class is taking that entire breadth of data and dividing it into a specific number of bins. So dividing it into a specific number of class groupings. So once you have that width, you would start with the lowest. And let's say you divided this by, say, in the example that you'll do 9 groupings. We decide that there are 9 bins. So you took that highest observation and that lowest observation and you created 9 different groupings between them. So these class limits are like the lowest to that first of 9 and then the second of 9 and all the way up to that top end of the 9th bin would be your highest observation. Then I go on to discuss the steps for doing these in Excel and in SPSS. So at this point, I'm pretty much just going to skip the actual directions because me reading them to you doesn't actually do you all that much good. What I would suggest is read through these so you have a general idea of what you're supposed to be doing, and then go and look at the questions that I'm going to ask you to practice on and that I actually give you the solutions for this chapter. So what you're going to do is look at returns to data, and you can find the link to that on Canvas. And what it does is it provides the annualized returns for a series of load and no load funds. And you're going to work through a series of, steps based on that. So the first question I ask you to do is develop the frequency distribution and associated histogram, and I show you how to do that in videos both on Excel and using SPSS. So the purpose of having the directions written out here on these PowerPoint slides is that when you print out the slides for notes, you can actually look at the steps written out step by step to follow along when you don't have the video right there next to you in order to go through and practice with this information. So I'm just going to skip through these slides here. Okay, descriptive statistics. So descriptive statistics are what we generally think about when we think of basic statistics. We'll have here the sample mean. It's a numerical summary of your data. It's usually, the first thing that comes to mind when people think of a descriptive statistic is the average. So it's the average or the expected observation. The next most common thing that comes to mind is the median or the midpoint. So the first thing that we have here, X bar, that's going to be your average. And you take the sum of the X's and divide by the number of observations. Now I've shown this here, X bar, that's for your sample, and mu is for the population. Now what we're going to do is use a sample to make inferences about the population. So in reality, you're never going to know large N, the number of observations in the population, but you will know small n, the number of observations in the sample. So in all the statistics that we're going to be calculating, we're going to be making hypotheses about mu, but we're going to be using X bar because X bar is actually based on our sample that we can actually gather based on which is from the population, but the population is way too huge for us to be able to actually gather all of that information. The next thing that we look at there is the variance calculation. For a population, it's sigma squared, and for the sample, it's S squared. Now, it kind of looks a little funny in this slide. There should be a line here dividing that summation divided by the quantity n minus 1. So I'm not really sure why that didn't come up very well in the slides. But so what we're doing here it's what I observe minus what I expected, so minus the average squared, and you're going to do that for all of your observations, and you're going to add them all up, and then you're going to divide by n minus 1. Why n minus 1? Because it's a sample statistic, not a population statistic. That's just something we have to get used to. But what is a variance telling us? I come from a finance background, so the first thing that I think about are, say, stock returns, and thus why you're using a stock return example in this first chapter. But when I think of average, the first thing, average or mean, the first thing that comes to my head is the average expected return. So I always think of variance as the risk of not getting what you expect squared. So xi is each individual observation, each individual return in any given year, minus its mean. So the difference between what I actually see, the return I see, minus the mean, the average, the expected return. And then I'm going to square that. Now, why am I squaring that? I'm squaring it because I want to measure risk. I want to measure dispersion. I don't want observations above the mean to cancel out with observations below the mean. So squaring that eliminates that possibility. So variance, in my mind, is the risk of not getting what you expect. And I'm going to add those all up. But again, thinking of, mean being in percentage notation, that means that my variance is in percent squared, which doesn't make any sense. I have no way of knowing how to interpret that. So what I actually interpret is the standard deviation, which is the square root of the variance, which we can then see in that next green box there. So the standard deviation is kind of a dispersion measure. So if I think of my normal distribution, it's going to show how spread out my observations are. Or if I look at my histogram, it's going to show how spread out my histogram is. If my sample standard deviation was really little, then I'm going to see a really narrow histogram. Versus if my standard deviation is big, I'm going to see a really wide histogram. So here's how to calculate descriptive statistics using Excel and using SPSS. Now, let's look at the information here about the normal distribution. We generally think of the normal distribution, you did lots of work with it in 260. We like the standard normal distribution. It's centered around the mean, so the mean is, the average, the middle number, and then if your data is normally distributed, then 68% will be within one standard deviation of the mean, 95% within 2 standard deviations, and 99% within 3 standard deviations. And we calculated, based on this normal distribution, we could convert it into a standard normal distribution, and we could get this z-score calculation. And we used the normal distribution to give us the probability for the random variables are given by the area under the curve. So the probability of getting at least as extreme a value as you actually observe, that's what our p-value told us. So the p-value is the probability of the data is as least as extreme as observed if HO is true, and that the probability of the variable is between 0 and z, and then we know the total area under the curve has to add up to 1, with 0.5 being to the left of the mean, or so 50% to the left of the mean, 50% to the right of the mean. So really understanding here what we can get from this normal distribution is we could have either a really wide or a really narrow, depending on how big your standard deviation is. So the smaller the standard deviation, the narrower this distribution. The higher the standard deviation, the wider this distribution would become. The central limit theorem says that as we increase the number of observations in our sample size, we approximate the normal distribution. So in theory, anytime n is greater than 30, you can use the z-score and you can use z-statistics. And I'll give you a link to a Khan Academy thing where they actually discuss that and state that. But in practice, no one ever uses z outside of statistics textbooks. Every hypothesis test that you ever do uses t. And the reason for that, even if, n is greater than 30, the reason for that, the reason that we use t instead of z, is that we don't know the standard deviation, or the variance, of the population. All we can do is extrapolate and estimate, based on our sample, what the standard deviation of the population should be based on our sample. So without actually knowing the standard deviation or variance of the sample, of the population, I can't use z. If I'm always just going to be approximating that standard deviation using my sample standard deviation, then it's appropriate to use t. Okay, so for practical purposes, we're always going to use t when we do our hypothesis testing. And here this is discussing confidence intervals of the mean. So, a question that comes up very often, I'm 95% confident that the average return is between A and B, where A is the lower bound and B is the upper bound, something like that. So in general, we talk about 95% confidence intervals because they're the default. And this is showing you this bottom equation, x bar plus or minus t alpha over 2 comma n minus 1 times s divided by the square root of n. What that's showing you is how to calculate a 95% confidence interval. So it says the mean plus some confidence level and the mean minus some confidence level. And that will give you the mean minus that confidence level will give you the lower bound of 95% or 90 or 99, whatever you wanted. And the mean plus that confidence level would give you the upper bound. And I just have that written out here in Z notation as well. One is showing plus, and one of these equations shows plus minus. One of them just shows minus and then plus in the same thing and is showing it in brackets. What I'm trying to do with this, and we'll discuss this in class, is get you over the initial, oh my god, equation, kind of reaction, which is okay to feel. That is perfectly fine. But the equations are there to help you. So I'm looking at these two peach boxes. Both of them are showing how to calculate a 95% confidence interval. One is using T and one is using Z. Other than that, they're saying the same thing. And you'll notice the Z one uses sigma because you know the population standard deviation. The T one uses S because you only know the sample standard deviation. But they're working in the same way. The only thing that's different is the notation. So the one in brackets that is using Z shows the lower bound, lower 95, comma, upper 95. Now I'm saying 95 and assuming alpha is 0.05 because that's what you do most of the time. You can change the alpha values in order to change your confidence levels there. Versus the second peach box says, mean plus or minus, but it's saying the same thing. I could rewrite that to look exactly the same as my upper peach box. And basically what I'm looking at here when I'm calculating my confidence interval, I'm saying that I'm 95% confident that my mean falls within this range. And then here's how to calculate the 95% confidence interval using Excel and using SPSS. Now, hypothesis testing. Okay, so we're going to talk about two different types of hypothesis testing here, using a single sample or using two different samples and comparing them. So we're going to start off with using a single sample. The null hypothesis is denoted HO. HO is the opposite of what you want or what you think should happen. HA is what you think should happen. So HA, what I think, HO, the opposite of what I think. Now, hypothesis testing is really, really weird because what we do, I think HA, So I test the opposite of what I think should be true. And my goal is to reject that the opposite of what I think is true. I want to reject the opposite of what I think so that I'm left with what I think. So your goal, you kind of state, I think that my grade is going to be greater than a 95%. So I test that my grade is going to be less than a 95%. And then my goal is to reject that my grade is going to be less than a 95%. So I will end up concluding that my grade should be greater than a 95%. So start what you think is HA. HO is the opposite of what you think. And then your goal is to reject HO so that you can conclude HA. A p-value is the measure of support provided by the sample for the null hypothesis. So a p-value is the risk of being wrong when you rejected HO, or if you reject HO. So you want that to be really low because you want the risk of you being wrong to be low. That makes sense logically, right? You want to be more right than wrong, so you want the risk of you being wrong to be really low. So you want your p-value to be low. So an easy way to remember this, and I know it sounds funny, but trust me, you'll remember it better if I say it this way. If p is low, reject the ho. Okay, so if p is low, reject HO. That's your goal, because p-value is the risk that you're wrong and you don't want to be wrong. So you want the risk of you being wrong to be really low. Okay. So hypothesis testing here. Here we have it all linked out. You always reject if p is less than or equal to alpha. Alpha I describe, and I have it kind of broken out here. Alpha is the acceptable degree of error, usually 5%, meaning you're willing to accept a 5% chance that your conclusion may be wrong. I think of alpha as the acceptable degree of screw-uptitude. So I'm like 5% willing to be wrong, but I'm not willing to be wrong more than 5% of the time. So I want to be right 95% of the time, and hence wrong 5% of the time, but we don't like to highlight that, which is why we talk about 95% confidence intervals. I'm 95% confident that the average is between X and Y, things like that. That's because alpha, the acceptable amount of error, is 5%. So if p is less than 0.05, we reject HO. The p-value tells the probability that you're wrong if you rejected HO. So you want it to be less than 5%. So if we go back here, if p is less than 0.05, we'll always reject HO. That's our general rule. In SPSS, we're going to call it significance. In Excel, we're going to call it p-value. Either way, you know that significance and p-value both mean p-value. Okay, so what we're looking at here are 3 different types of tests. One rule to remember, HA is always what you think should happen. So you test HO, the opposite of what you think should happen. Second rule, the HO always has to be equal. So in your two-tailed test, HO, your average equals some given average. In your one-tailed lower test, HO, the average, is greater than or equal to some hypothesized average. So the or equal to is on there, and you'll see that in the one-tailed upper test as well, the or equal to. So HO always has to have the or equal to. That's a rule. Okay. Now, one-tailed upper, one-tailed lower. How do I distinguish? How do I remember between the two of them? Two-tailed's easy. It's the one that has the equal sign. How do I remember between one-tailed upper and one-tailed lower? So greater than means lower tail. Less than means upper tail. So you can remember it as the opposite of what you think. Or we can go down here and we see the lower-tailed test. So if p-value is less than alpha, you would reject HO. So you reject HO in the lower tail. So you rejected HO. Remember, HO, go back here. HO is mu is greater than or equal to your hypothesized value. We're doing this one-tailed lower test. HO mu is greater than or equal to your hypothesized value. So you reject HO in the lower tail. In the upper tail, you would not reject HO. You would be finding that HO was not in fact violated. So you can either remember hypothesis greater than means lower tail, and you could just remember it as like an opposite kind of thing, or you can look at it and say it's the lower tail because I'm rejecting HO only in the lower tail. If it was in the upper tail, then it would be consistent with my hypothesis. Since my hypothesis was HO mu is greater than or equal to my hypothesized value. So then the opposite would go for the upper tail. The upper tail test would be HO is less than or equal to your hypothesized value. So you would not reject in the lower tail, but you would reject in the upper tail. So the upper tail is what, when it says less than, you would reject in the upper tail. So I don't know. I'm just trying to think of ways that memory trick could work. So you can either remember the opposite, or you could remember that you would reject in that tail, whatever works for you. And then your p-value 2 tail, you're testing, is it equal to something? So you believe it's equal to that value, and you're testing, you would reject if it's on either tail, either above that or below that value. So here's how to calculate your hypotheses, your hypothesis testing using Excel. Now, I give you the information for both T and Z. However, I'm really only ever going to test you on T because in reality, you really never know the standard deviation of the population. So there's no simple hypothesis testing thing that I can set up in Excel. What I'll have to do is basically just apply that formula. So the mean minus the hypothesized value divided by the quantity standard deviation divided by the square root of number of observations. This denominator, standard deviation divided by the square root of number of observations, is known as the standard error. Okay, so what I did here is I set up how you would set up a hypothesis testing table in Excel. First thing I do is define all of these variables, then stick them into the t-statistic, and then get Excel to calculate the p-values for you. So count gives you that n. Average gives you that x bar. STDEV gives you that s. The standard error calculation that I have to hypothesized value is the next thing. You just enter the hypothesized value. That's mu 0. Then standard error, that just says calculate the denominator of your t equation here. So standard deviation divided by the square root of the sample size. So STDEV divided by square root of that count variable that you calculated up there. Then the t-statistic. Okay. We're going to make the t-statistic an absolute value. That way you don't have to worry about strange things that can happen in Excel when you use t-dist versus t-dot-dist and all that stuff. Just make it absolute value. So absolute value of the mean minus the hypothesized value, and that divided by the standard error. Now, you don't have to separate this standard error, do that denominator on a separate line. That's not required. You can choose to do it that way if you want, and I show in the video it going both ways. Then t-statistic is, the p-value lower is calculated using t-dist, and then p-value upper, 1 minus p-value lower, and p-value 2 times the minimum of the upper and lower. Now, I'm going through this specifically because I don't know what you've seen. I know this is pretty similar to what most of my students have seen in 260, but I don't know what you've been presented with in the past. So I just wanted to go through that. The Excel video does go through it at a slightly more extensive, and it obviously makes a lot more sense because you're looking at Excel data when I'm talking about it. Okay, so here are the directions using SPSS. Now, what's interesting here is that SPSS always does the two-tailed test by default. What then happens is you have to convert. If you're doing HO mu equals something, then you can stop right there. You look at the significance two-tail, that's your p-value for the two-tailed test. If it's less than 0.05, reject HO. If it's not less than 0.05, do not reject HO, and you're done. If, however, you were doing a one-tailed test, then you have to be a little bit more concerned. You have to convert that two-tailed into a one-tailed. So I have it written out here. For the one-tailed test, it's that p-value divided by 2. Significance two-tail is a p-value divided by 2. If t has the same sign as the tail that you're looking at. So if you want to do an upper tail test and your t is positive, then just take the p-value and divide it by 2. If you want to do a lower tail test and your t is negative, then just take the p-value and divide by 2. But if you wanted to do an upper tail test and t was negative, or you wanted to do a lower tail test and t was positive, then you would have to do 1 minus the p-value divided by 2. So that's just something you're going to have to practice with. In general, know that SPSS automatically gives the p-value two-tail, and it's given as significance two-tail. If you want to do an upper tail test and t is positive, just take it and divide it by 2. If you want to do a lower tail test and t is negative, just take that p-value and divide by 2. Otherwise, it's 1 minus the p-value divided by 2. So if the tail matches your sign, just divide. If the tail does not match your sign, then 1 minus p-value divided by 2. Hypothesis testing with comparing two different sample means. So in the example that I have you working on here, you're going to be looking at your load versus your no load funds, and you're going to be testing HO, they have the same return, or HA, they do not. So there's two different ways of formulating this. Either the returns are equal, or saying the difference between the returns is 0, which is the same thing as saying the returns are equal, essentially. In SPSS, you'd follow the exact same logic using the p-value two-tail and converting it to one-tail and all of that. Obviously, the two-tail test you wouldn't have to convert, but for the one-tails below, you'd follow that exact same process. All right, so let's look at this. What exactly does this do? The two-tailed test statistic basically just the t-value is the two means subtracted from each other. And that standard error, that denominator, is the standard deviations divided by the number of observations, and then the square root of all, the variances divided by the number of observations, the square root of all of that. It's basically saying the sum of the two standard errors, because the standard error is the standard deviation divided by the square root of the number of observations. So by squaring those standard deviations, it just moves you to the variance, and then when you take the square root of that, you're going back to that standard deviation. So here's how to do it in Excel, and here's how to do it in SPSS. Now, SPSS is going to be a little bit odd here because of you're going to have to reformat your data into two different columns. One column just listing the actual observations, and a second column denoting which observation or which group that observation falls into. And you'll see a discussion of that on the video.